first let's review quickly what centripetal force is. So as you know, right, Newton's law say that F equals to ma. And what is A? A is the second derivative of A is the second derivative of position, and position consists of three components, right? So this is second derivative of x, y, and z, right? And of course, force is also a vector, so force is also fx, fy, and fz. So basically F equals ma is a vector equation, and we can think of it component wise, right? So you can think of it component wise. This for x component and likewise for y and z, right? So what this means is that if we apply zero force, right, in the x component, then x is at most linear in time, right? And basically that corresponds to x having a constant velocity. So basically this means is that if your force in the x component, so let's say I have a particle over here, and let's say okay, let's ignore the third dimension for drawing purposes, okay? But let's say it have a force over here, and there's a coordinate system x and y, right? And if I don't exert a force in the x direction, right, and that means the force is only in the y direction, right? So these are the forces acting on it, F1 and F2. If I only exert forces in the y direction, right, and force in the x direction is 0, then the velocity, the x velocity, right, the x component of the velocity would stay the same, right? And so this tells me that if I don't apply a force, I have a constant velocity. But the other way could be true, right? Meaning that if my x is, let's say, if my x component, right, of position is linear with respect to time, or if it's even better, what if x of t is constant, right? Constant. Right? If x of t is constant, then that will imply that the second derivative is 0, and that will imply that I must have no force acting in the x direction. Okay, so you can see that this Newton's third law, right, tells that's right, Newton's second law, F equals ma, in the Cartesian coordinate system, right? In the Cartesian coordinate system, tells us that if my forces in some component, some direction, right, is 0, then the coordinate, right, is at most linear in time. And if my coordinate is constant, then that means my force must be 0 also, right? And this is a feature in the Cartesian coordinate system, and it's due to the fact that the Cartesian basis is constant everywhere, right? So what do I mean by this? This means that if let's say I go to a coordinate system where let's say I go into the polar coordinate system where the r and theta coordinates are the radius, right, from the origin, O, and theta is the angle it makes with the horizontal. If I go into this coordinate system r and theta, then it turns out that that in general, right, f of r, if I work out the equations, right, and you can see the derivation here in another video, right, if I work out the equations, I'll actually get that f of r is equals to m second derivative of r with respect to time minus r first derivative of time squared, like this. Okay, so we realize that, okay, if I simplify it, if I write it in a more compact notation, I'll actually have this, right? Which means that, wait, this is a bit different now, right? Previously, let's compare this equation versus f of x equals to mx double dot, right? This told us that if my x coordinate is constant, right, x of t is constant, it's a constant function of time, then that implies that f of x equals to 0, right? It's equals to 0. There's no force in the x component. But now, if I have r double dot, right, if I have r is a constant function of time, right, that doesn't imply that f of r equals to 0. In fact, r as a constant function of time, right, this term will cancel, will disappear. It actually implies that f of r is equals to minus r the dot squared. This means that if, let's say, right, I had a particle, and let's say I told you, please keep the particle at the same x coordinate, right? You can let it move in the y coordinate, I don't care, but please keep it the x coordinate, same x coordinate. Then you just jolly well make sure that you do not apply a force in the x direction, so you move purely in the y direction, right? But if I give you a particle and I told you, please, pretty please do not change the r coordinate, right? Please keep the r coordinate constant. Then what kind of force will you have to act, right? You actually have to act a non-zero force in the radial component. And what does that look like, right? In the radial component, we know the radial component points away from the center, right? If you're not sure about this, check out the lecture on basis vectors. This diagram should make sense, right? So that will actually mean that will actually imply that f of r, if I want to keep something in the at the same radius, right, same radial coordinate, that will mean that I actually have to apply a force that is acting inwards, right, and it's inwards because of this negative sign. And this force, right, is known as the centripetal force. So the centripetal force, right, if I put it in English, it is the force required to keep the object at constant radius. Okay,